Thank you very much for inviting me. So I'll be talking about what we call generalized charges, which goes in line with generalized symmetries. And the idea is that we want to understand how these symmetries act on operators in quantum field theory. And then various possible actions are the various possible generalized charges, just like the usual charges are the various possible actions of the usual symmetries. And then these generalized charges can be used for a lot of physical applications of generalized symmetries. And so let me begin with a little bit of an introduction, some overview of what I have in mind. So we want to discuss generalized symmetries to begin with. In which I include the most general kind of symmetry I want to include are non-invertible symmetries and relativistic quantum field theories. So we have some generalized symmetry. And as by now it has been well appreciated that the mathematical structure which governs them is that of fusion higher categories. So if you want to specify a symmetry of a theory, you want to specify a fusion higher category. And this, how higher it is, depends on the dimension of the space-time that you are working in. So if you are working with space-time dimension d equals to 2, such as you're looking for fusion 1 categories or just usual fusion categories. And if you're working in general space-time dimension, then there will be a fusion d-1 category. And I would put a disclaimer here because of fusion. I mean, so I'm only studying finite generalized symmetries, which have some appropriate finiteness. So, I mean, the basic idea is very simple, why these categories appear in the description of symmetries. So we know that symmetries should correspond to topological operators in a quantum field theory. And then you can consider various kinds of topological operators graded by their dimensionality. So you can begin with d-1 dimensional topological operators. So this is some topological operator which is d-dimensional. D-1 dimensional. So codimension 1 in space-time. And the spectrum of these topological operators is the spectrum of objects in this fusion d-1 category. And then if you have two such operators, you might want to study topological operators going between these two, which have codimension 2. And the spectrum of these is the spectrum of morphisms between the corresponding objects. And you can continue in this fashion if you take two of these codimension 2 operators, then you can have codimension 3 topological operators between them, which will be two morphisms. And so on, you get higher morphisms. So that's how you build a d-1 categorical structure. And there is a fusion structure, which is coming from the fact that you can stack them together using the extra direction that I have in spacetime. So that's the brief review why the mathematical structure is that of a fusion higher category. And now we want to understand that given a fusion higher category, how can it act on operators in a theory? So this symmetry might be realized in different theories, and it might have different actions on operators in those theories. So we want to understand all possible actions that are there. Yeah. Yes, finiteness is related to the fact that I have fusion category rather than a general monoidal one. Well, you can try to mathematically at least try to define. You can have monoidal higher categories. You can try to impose other conditions on them. There are also some technical conditions when I say fusion, and whenever I go to 2 categories and higher, which is about Karubi completeness. So you may want to include that or not, which physically means whether you include condensation defects or not. So there are various notions. That's why I want to like fix myself to this realm of fusion higher categories. Not necessarily, yeah. But the things I will be discussing, it won't be important. I mean, if you have two equivalent categories, one of them is strict and the other is not, it will be, yeah, it won't matter in these calculations, the considerations that we are going to consider. So equivalent categories are going to give equivalent results. So, oh, sorry, I cannot move here. Yeah.
This framework, so let's say if I'm in D,
yeah.
where the objects as the surface,
yeah,
and the lines as like,
yes.
So when we normally talk about like a modular tensor category, we are somehow compressing the surface.
Yes. So you are looking at endomorphisms of the identity object. Yeah. So indeed, there is starting from a modular tensor category, or in general, a braided category, you can construct the modules of that category. These modules form a 2 category, which describe the surfaces, and the endomorphisms of the identity module are these, the braided tensor category. Yeah. And that actually just includes condensation defects constructed out of the braided tensor category. Yeah. Okay. Right. So now we want to understand, given a fusion higher category, what are the possible actions it can have. So we very well know some of the actions. So for example, if I just have the most standard symmetry, so if I have a usual group-like symmetry, given by some finite group G, which may be abelian or non-abelian. And it's also known in high energy physics as a zero form symmetry. So then we know what the charges are. There are some usual notions of charges. So we say that we can have local operators, zero-dimensional point-like operators in the theory. And then these symmetries, the charges of these operators are just representations. So there are some representation R inside the category of representations of the group. And it's easy to see why that's the case from this kind of considerations from the topological operator point of view. So what you want to consider is you want to study that if I have a point-like insertion, so there is some vector space of point-like insertions I choose, which is V. And then I take one of these operators. So I have a codimension 1 operator in this case, which is labeled by a group element G in G. And then if I slide it past, what happens? So it's topological, but there is some non-topological nature that might arise when it passes another defect. So this, in general, will be equal to some other vector. So if I had chosen a vector V in V, this will be some other vector G dot V in V. And so you obtain an action of G on this vector space. And from this, you conclude that this vector space must form some representation. And so that's how you just simply classify all the possible charges in this case. Yeah, the underlying vector space of R is V. Yeah. Okay. Now, what has not been very well appreciated is that these usual group-like symmetries can act on even high dimensional operators, not just point operators. So let me describe a little bit about that. So you might have actions of this type. You have a line operator, and then when it passes through one of these codimension 1 operators, so let's say some line operator L, then it might be permuted to some other line operator. such that now there is some set of line operators I'm considering on which G acts as permutation. So this can happen. For example, probably the simplest example is to take a Wilson line operator. So let's say you have a U1 gauge theory. You have Wilson line operators labeled by charge Q, gauge charge Q. And then the charge conjugation simply sends charge Q to minus Q. So it has an action like this, which would mean that L is WQ and L prime is W minus Q in this case. And there is just one non-trivial element in Z2. Okay, so now one may ask, is this all the possible charges of line operators can carry? Is it just a permutation? It turns out it's not quite the case. So mathematically, you might already try to guess an answer. So point-like operators were representations of G. So you might ask, are there things like two representations of G, which are some higher categorical analog? So just like rep G forms a category, whose objects are representations and morphisms are intertwiners between representations, is there a two category which extends it? And there is indeed very well studied this fusion two category to rep G. So this might be a natural answer, but we need to justify it using physics. It indeed turns out to be the correct answer. Okay.
Another possible action that you can also line by surrounding the line by topological operator.
Right.
How do you see that the two are the same?
Yeah, because when you surround it, you can then think about all the possible lines that you will get can be obtained by performing these sort of cigar fusions with the line. So just imagine folding it in this direction. So
the compass line.
Mhm.
Three-dimensional, you have a cylinder.
Right. Right. So when it's invertible, there will be a single line, but when this is non-invertible, there might be multiple lines. So indeed, then you in general have to consider a sum of lines here with many kinds of operators that can appear. So I'm here using the fact that I'm in invertible world. So in that case, when you do the cylinder, you'll just obtain a unique line. Okay. Okay. Yeah. So I'm saying that the answer is two representations of G. And what is this extra physical information? So let's study a little bit more of this action. Let's fix a line operator L in this set. So let's pick a line operator L. Now, in general, it may be permuted, but there may be some subgroup that leaves it invariant. So you might have situations where as L goes through some UH, where H is in some subgroup H of G, then L is left invariant. Now, is there some finer action encoded in these local operators is the question. So now you can view these local operators living at the junction of this codimension 1 surface and the line. These are topological, so you can view them as generating another group-like symmetry which is localized along this line. So it induces some symmetry on the line. So there is an H-induced symmetry on the line, which is again a zero-form symmetry. Because it obeys the group multiplication, but it might not quite obey it. So in general, what may happen is that there may be some anomaly for this induced symmetry, some 't Hooft anomaly. So when you bring two of these together, so say H1 and H2, where the line L remains the same, and let me call these zero-dimensional operators as D0H and D0H1, H2. So although the bulk operators are guaranteed to respect the fusion, the H fusion, these junctions may not. And there might be some extra phase that is left over. So this might be equal to UH1, H2. But here you have D0, H1, H2. times some phase. And then this just simply means that on this one-dimensional line, you have a zero form symmetry H, but that has a 't Hooft anomaly. So you can read precisely what the 't Hooft anomaly is from these coefficients. So these coefficients will describe for you an element alpha in the second group cohomology of H, valued in U1. The co-cycle condition comes from the fact that from the associativity of this action, and the extra redundancy comes from the fact that you can scale all of these operators by some U1 numbers.
This here, then it's like projective representation.
Yeah, it's a project.
Yeah, or parts.
Right. Right. So, right. So there.
Is this a datum of the G symmetry, or is this? It's not related to an anomaly of the G symmetry.
Right. It's a datum of a line operator of a charge of yeah. So a line operator like this may be in your theory or may not be in your theory. Just like a point operator carrying a charge may be in your theory or not. Right.
But you're assuming all this that the G symmetry is anomaly free.
Yeah, I'm assuming G symmetry is anomaly free. You can extend it to anomalous cases. Wait, so you can have an anomaly if the dimension is large enough. So if dimension is 3 or larger here, then it's fine. This analysis goes through, but not for dimension 2. So there's just you need to have a gap of 2.
Why the assumption of what the G is anomaly free?
Right. So if you were to do this in dimension 2, you have to in general consider configurations which are like this, of this form, right? L, UH1, and some L prime in general. So you can end things, and then there is a two-sided information you need to provide. Here I'm assuming that it's something that cannot end on the line. My zero form symmetry generators cannot end on the line because they have an extra dimension. Yeah, in 3 dimensions, they're 2 dimensionals. Yeah, and so they can just pass through. They have an extra dimension. They have to pass through the line. So it's just a technique. If you can do analysis in 2 dimensions, the result will be different in general. Yeah. Is it okay?
I'm not understanding where the vanishing of the dot anomaly enters in saying that you have this phase. I mean, it seems that it can also the anomalous.
Yeah, that's what I just answered. So you can have anomaly if D is greater than or equal to 3. So this analysis is valid for G with anomaly, for D greater than or equal to 3. Yeah. It's some operator which lives at the junction. So it's in this. No, yeah, it's not. It's forming more like a projective representation, as you remember. Yeah. Yeah, it's operators acting on a projective representation, and the vectors of the projective representation will be realized at the ends of this line, which I'm not going into today. Yeah, I'm coming to it. Yeah. So yeah, alpha depends on L. So we are just trying to understand what are the possible actions one can have. And then we find that they're parameterized, first of all, by a subgroup H of G, and then an element alpha in the second group cohomology of H. And now if you go to mathematics literature and ask what is 2rep G, you find that it has simple objects which are precisely classified by these 2 data. So let me give a few words on what 2rep G is. So just like rep G is trying to have G actions on vector spaces, so you study problems of this form. Now in 2rep G, you want to understand how G can act on say semi-simple, finite semi-simple 1 categories. So all these possible actions then describe two representations of G. And that's just isomorphic to understanding these kind of physical questions, this description. Yes. Mhm. Yeah. Yes. To 2vec. Yeah. 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 That's correct. Yeah. Mhm. Sorry, in what case? Yeah. Right. Or it would be one. So one morphisms will be group elements. So you want to have a vec G inside this thing. Yeah. So yeah, I should have said this. This is more precisely treated as vec G. So you have the single object which picks up the category under this 2 functor that he described, and then one morphisms are vec G, and then you need to represent them on the one morphisms of this category. Yeah. 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 Right. Mm-hmm. Yeah, but you need to represent it, right? This functor needs to so whatever associator you had, that needs to be represented on the target category by the functor. Yeah. Okay. So yeah. So this is precisely 2rep G. So there's already something very interesting that when you go to start studying charges, even for usual group-like symmetries or zero-form symmetries, you can have higher charges. So now we can start labeling charges by an integer. So let's say the 0-dimensional operators, the way they can transform are the possible 0 charges. These are given by representations of G. And how line operators can transform, which we discussed over here, these are the possible 1 charges. And now you might ask, what are the possible 2 charges and higher? And there is a natural mathematics guess, which is that you replace 2 there by 3. So you have 3 representations of G and so on. So indeed, that turns out to be correct. And that encodes a lot of interesting physics. So you can now generalize this to 3rep G. These would be 2 charges, or how surface operators transform. And this will be describing, so let me use the functor language. So it would be from a 3 category based on a group. You would be looking for 3 functors into 3vec, which is, and then you have 2 choices over here. You might want to have this to be Karoubi complete or not. Karoubi complete one has an infinite number of simple objects. So there are infinite number of simple or irreducible 2 charges and so on. So when we discuss 0 charges, there were a finite number because there were a finite number of irreducible representations. Similarly, for 1 charge, this is finite information, but there's an infinite amount of information that starts coming in over here. And that is essentially tied to the fact that there are an infinite number of fusion categories. Yeah, so it's similar to what we just discussed. It's now you want one morphisms to be the group, and so you get a two vec G kind of category, and you look for maps into some two category inside 3vec, some object of 3vec. Yeah, G appears as one morphisms. Yeah, that's what I was saying. Yes. Yeah. Yes. Mhm. Yeah, it was the same. You take the two category based on G to 2vec. Yes. Yeah, right hand side is also the most trivial category you can construct, which is Karubi complete. Yeah. Yeah, so let me give references for this work. Coherence data. No, I don't know about references for coherence data, but I can give references for all this work. So it appeared in our paper with Sakura. It's called Generalized Charges, part 1. And there's also a related paper by Thomas Barsh, Matt Bullimore, and Andre Grigoletto, who is here, which appeared around the same time. Right, so, sure. Yeah. Yeah. Right. So, let's see.
I guess the thing is consider this universal targets constructions by the Johnson, Fried, and Reuter, and I guess once you restrict to that, you will indicate like sigma models dimensions 2, 3, then very universal. Okay. That's part of the
Yeah, thanks. Yeah, so I want to discuss now maybe some examples of interesting two charges. So not there. So yeah. So you might think of two charges, which are three representations of G, as being parameterized by G graded G. So let me write it on G graded fusion 1 categories. So a Morita class of them describes different inequivalent objects in 3rep-G. So now you may ask, where does this G graded fusion 1 category appear in the description of action of a G0 form symmetry on surface operators? So this is the picture. So you're considering some surface, arbitrary surface that you have. Now there may be topological line operators living on it. And as we have discussed already, if you're in two dimensions, the topological operators form a category, a fusion 1 category. So here on this, you obtain a fusion 1 category, which is living on it. And now in addition to it, when G crosses it, you obtain lines which are living at the junctions when G crosses it. So then for each UG, for each element G in G, you obtain another one category of lines such that their fusion respects the G grading. So when you combine together the lines which are living on the surface along with these lines living at the junctions, you obtain a G-graded fusion 1 category. And there can be many interesting, a lot of interesting physics encoded here. So let's take an example. So you can have a fusion 1 category given just by vec Z4, which means that you have a total Z4 worth of lines, but the grading is Z2. So the trivially graded part is vec Z2. So it's like a group extension. So what this means is that on the surface S, you have a Z2 symmetry, a Z2 localized symmetry, a zero form, but that is localized. So all the line operators that live here cannot be taken out into the bulk. They're localized on the surface. And in addition, when you use the non-trivial, and here I'm using a Z2 zero form symmetry in the bulk. So G is Z2 as well. So when I take the non-trivial D minus 1 dimensional operator, I obtain two line operators living over here, L1 and L3, which are topological. And let me call the trivial line as L0 and the non-trivial line as L2. Then it follows the Z4 fusion rule. So if you fuse L1 with itself, you obtain L2. So these lines extend the lines living on the surface. So now you can see that there is this induced symmetry from the bulk. It's not quite Z2, like in the case of the lines, there we had a subgroup of the group G. These induced symmetry can start talking to localized symmetry. So there's a new physical phenomenon that when you go to surfaces and higher, you can have localized symmetries. And these localized symmetries can interact with the induced symmetries from the bulk. And this whole information is encoded in these higher representations, how they combine together.
An example of physical theory.
Yeah, right. Yeah, I think you can construct them by coupling in conformal theories to some higher gauge fields. I can't construct one at the moment, but we can discuss probably later. Yeah, is no S is a non-topological, so I want to take some conformal theory and couple it to some higher gauge, some discrete gauge fields in the bulk. Yeah, Z2 lines might be in the conformal theory itself. Yeah. 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 No, it's a G-graded fusion 1 category. No, the G is our original zero form group in the bulk. So yeah, and there is another extension. So you can have, you can take the E-sync fusion category, which is non-invertible. So there can be non-invertible extensions, which then projects to a Z2, and there is a Z2 which is inside. So it can be these sort of extensions, which are categorical extensions. And here what will happen is that you have the same surface. You have a Z2 symmetry on it. So you have L0, and let me call these lines as 1 and P. But when this non-trivial surface, Z2 surface intersects it, then there is a non-invertible topological line, S, that appears here, such that it obeys the E-sync fusion rule. So S squared is 1 plus P. So it's a non-trivial extension of the Z2 living on this by the Z2 in the bulk, into a non-invertible structure. Okay. This is any general D-dimensional theory with a two-dimensional surface operator.
So here the model lives on the two-dimensional surface.
Yes. Yeah.
It's not on the three-dimensional one.
Yeah, a higher dimensional bulk. And we have a two-dimensional surface, which can be topological or non-topological, on which this symmetry acts, the bulk G0 form symmetry act. And the action is described in terms of how the various topological operators combine together, the one living on the surface and the one living in the bulk, which is this sort of extensions. Right. Okay, so maybe I should have already mentioned examples here for interesting two representations, like with non-trivial alpha. So you can obtain non-trivial alpha whenever H2 Z2 times Z2 U1 is non-trivial. The simplest the simplest group is Z2 times Z2, in which case this is Z2, and you can realize the non-trivial element of this 't Hooft anomaly in 3D pure SO4N theory. But I won't go into the details. You can look into our paper for the details.
The idea is that you have G, then you have some codimension something defect, and then you induce some kind of N category, which is created by G on
Yeah.
defect. You have the consistency data there, which give you the error representation.
Right, right. So higher representations, if you go even higher, they should just be G-graded fusion higher categories.
It's very non-trivial because told before that you can extend this to the case in which G is anomalous, no? And there should be some non-trivial consistency conditions between the data of the
Right, but they appear at codimension 1. If by anomaly you mean the anomalies which are localized at points, so the usual group cohomology type of anomalies, yeah, then it's it only affects the surfaces in codimension 1. So that's why I'm always keeping a codimension at least 2. So when I'm considering surfaces here, I want dimension to be at least 4.
But I mean, I can imagine taking the configuration which produces the G anomaly, some field,
Right.
and passing through the defect.
Yeah, but it will have no impact on it. Will just pass through it. Yeah, it can go around. Yes. Yeah, so if you take G-graded fusion 1 categories and up to Morita equivalence, they will give you different inequivalent objects. So this is just a description of 3 representations. Yeah. 2 representations are classified in terms of this information that I wrote down. It's a subgroup and that. Yeah. 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 Right. Yes, sorry. Yeah. You can have multi-fusion as well, and there's an extension of this. Yeah. Yeah. So this is like, yeah. But I think all the essential physical ideas are here. Yeah. So now I want to extend this story to general symmetries. So we want to now go to, but before going there, we can start generalizing our symmetries step by step a little bit. So the first generalizations which became popular were higher form symmetries. So let's say we have a P form symmetry. They are again described by some group, some finite group G. But now the codimension, the operators are codimension P plus 1. Okay, and in this case, there is a natural generalization of the higher representation classification. So you can regard, actually we can treat two things in the same way. You can also consider P groups, which combine various higher form symmetries. So a P form symmetry can be regarded as a P+1 group, a special type of P+1 group. And in general, a P+1 group will have 0 form symmetries up to P form symmetries, which mix with each other. So here you have 0 form, 1 form, up to P form symmetries. And then they can non-trivially extend each other or act on each other. Okay, so and if you just keep the last level of P form symmetries, while all the others are trivial, you obtain a P+1 group based on the P form symmetry. So we can call this group as now a P+1 group, which is based on G, the P form group G. So now there is a natural generalization of higher representations to higher groups. So again, you just change the source category. So there were just some functors from a source category, which was built from a source higher category, which were built from the data of a group, but you can also build similar categories from the data of a P+1 group. And the target category remains the same. So it will be some Q vec. So let's see, I want Q+1 vec. And this is also Q+1 category. And such functors classify what are known as Q+1 representations of this P+1 group. And these are precisely physically the Q charges or Q-dimensional operators. The action of such a P group symmetry, P+1 group symmetry on Q-dimensional operators. And then you can study what these sort of functors are, and they're interesting. What is the physics they encode? Let me discuss just some aspects of this. So you can find the general story in the reference I mentioned earlier in Generalized Charges Part 1. Yeah, yes. So here there is a restriction. If you are in P-form symmetry case, yes. Because the first level where they act are P-dimensional operators. This is what is well known. So yeah, this is an important point. So say we were in this case, in this type of P-form symmetry. Let's put a P here. So if we are in this case of P-form symmetry group, then we know it's well known that there can be P-dimensional operators on which transform in representations of. So they live in representations, whose charge lives in the representations of this P-form group. So for one form symmetry, one says that line operators are charged in the representations. Yeah, and so on. For a two-form symmetry, surface operators are charged, and etc. So these are the well-known statements, but there can be higher charges. And these higher charges are encoded in these representations. So in particular, if you take Q to be P, you will essentially obtain representations of the group. Which in this case, because this needs to be abelian for higher form symmetry, this is just the group of the Pontryagin dual group. So, right, so that's an important point. But I want to discuss, this is of course encoded in this classification, but I want to discuss the simplest generalization. So a two charge of a one form symmetry. So we know there are one charges which are just characters of the group. So two charge will be a surface operator. So we want to understand how it can act on surfaces. And now again, there is a similar story. So you might want to see how this one form symmetry is induced on this surface operator. So you have some bulk codimension 2 operator, it can intersect in codimension 2 along the surface. And when it intersects, there can be many interesting things that happen. So let's say it intersects and goes through. At the intersection point, there might be various topological operators living on the surface that might get attached, that might just need to be there. So it might source those symmetries. So some operator, let's say some line operator, topological line operator living on the surface. So it may or may not induce such things. Moreover, so this is one of the physical phenomena that can occur. The second one is, let me go to the case where there is no induced symmetry. Then there can be line operators can act on these local operators, these junction local operators. So these local operators might themselves carry zero charges under the localized symmetry. And the combinations of the two. So there are induced symmetries. So these G1 can induce localized symmetries. And then the induced G1 symmetries themselves, which are these local operators, might be charged, can be charged under localized symmetries. Yeah.
There is one, so you had a concept of like permuting the lines.
Yeah.
Line one side and exit on the other side.
Right.
Permute the lines.
Yeah.
Subgroup the stabilizer of the substring.
Yeah.
Here it seems that you cannot have permutations of the surface.
Right.
No,
so all the representations are one-dimensional in some sense, which already holds true for the lowest charges as well. All these representations are one-dimensional, and the higher representations are also one-dimensional. They do not include multiple surfaces.
in this case, there is no subgroup as a data of the area.
Yeah. Yes.
But they can still be projected in some way.
Uh,
Before you add the points.
Yeah, the points may be projective when you take. Yeah, so that's the third point. Again, some projectivity, anomaly, 't Hooft anomaly. So this is essentially the physics of two charges of one form symmetry. Yeah. That's the one of these again this de-looping kind of categories. Yeah, then a zero form symmetry group, then one form symmetries at the two morphisms and so on. Yeah. It's just how much de-looping is there. Q just tells you how much de-looping you have done. Please go ahead. Yeah.
What in the rig group figures that the left hand side is always one. Yeah, for TFT, yes, but now he already deals with TFT. But the left hand side doesn't become
Yeah, in some sense it doesn't, but yeah, we can discuss it later. Yeah, it's the same as in zero form case. When there are higher morphisms that you add, which are trivial, but they change the structure quite a bit. G1 morphisms and then trivial. Yeah, yeah, is the similar here. Yeah.
You can have a sense of how strict they are. So, like when you say it's how strict.
I have no idea about strictness.
They have, are they defined with associators?
Yeah, they have associators in between. Yeah. Okay, so let me, don't have much time. So let me continue with, yeah. Yeah, I agree with you. Yeah, yes. Yeah.
But that requires like
Yeah. Okay. I assume all the nice conditions from now. Yeah. So now, yeah. So we want to generalize even further. So far, we just consider invertible symmetries. But now we want to also include non-invertible symmetries into the game. So we want to have a symmetry, which is a general fusion higher category. So if you're in D dimensions, it's a fusion D-1 category. And perhaps to keep ourselves grounded, we want to put D equals to 2. That's the simplest case where we are, many of us are familiar with fusion 1 categories, where there are interesting examples. So let me discuss some examples. When D is equals to 2, there are some interesting non-invertible symmetries like representations of S3. There are 3 representations, 1, 1 minus, and E. This is the trivial, this is a sign representation in which the Z2 subgroup acts, but the Z3 cyclic permutations do not act. This is a permutation group of 3 objects. And this is a 2-dimensional representation. So you have 2 vectors. There's a nice basis in which cyclic permutations act as omega and omega squared, while the Z2 transposition interchanges the 2 vectors. So that's this E representation. And there is a non-invertibility. So you have E squared equals to 1 plus 1 minus plus E. This is the tensor product decomposition. So this will be one of the examples I will want to focus on. And the second one, so as Yunchin already discussed, this is group theoretical because it can be obtained by gauging just an S3 group symmetry. So not so interesting, because if you understand the gauging, then you understand all of the physics. It's just a reorganization of the physics of group. But that process itself can be non-trivial. Okay. But then there can be categories which are not group theoretical, which cannot be obtained from groups, like the E-sync category, which is also the Tambare-Yamagami category based on Z2 with a particular choice of sign of square root 2. So this one has 3 simple objects, 1, P, and S. And the fusion rules are PS equals to SP is S, P squared is 1. So P generates a Z2 subsymmetry of E-sync. So note that there was also a Z2 subsymmetry here. But the non-invertible element distinguishes them. So here the non-invertible element squares to 1 plus P. It doesn't include an S, unlike here. Okay, so these are the 2 simplest cases that I would like to focus the concrete results on. But the general theory would be applicable very generally. Okay. So let me begin with the general theory, and then I will describe these 2 cases. So the idea is as follows. There is a general principle that if you have a quantum field theory in D dimensions, on which there is a symmetry that acts, some fusion higher category, then you can resolve it into a D plus 1 dimensional system. So this is a quantum field theory. It may or may not be topological. You can resolve it into an interval compactification of a D plus 1 dimensional TQFT, which is topological. That depends only on the symmetry S. So let me call this Z of the symmetry S. And then I need to provide boundary conditions for this TQFT on the interval. This is also related to what Wenjie talked about earlier. This is known as the symmetry TFT of S. And then on the left-hand side, we have what is sometimes known as the Dirichlet boundary or a regular boundary. So there is a topological boundary condition of the symmetry TFT. Let me call it sim because it encodes the symmetry. And the symmetry it encodes is S. So all the S symmetry is now acting here. So all the topological operators generating the S symmetry are now localized on this left boundary. And the rest of the dynamics is now on the right boundary. So this is some non-topological. If the theory is non-topological, this is non-topological. If the theory is topological, this boundary is topological. Non-topological, yeah. I mean, so this is a, let me call it the physical boundary. All right, thank you. Right, so this is the general picture. And then this interval compactification can be taken because this the left side and this bulk is topological, so you can just slam this onto the right boundary. Okay. So given this general picture of symmetry TFT, it's quite easy to see what generalized charges are. So let me discuss that.
Thank you. In general, S is a D-2 fusion category, and BS on the left-hand side is that.
S is a fusion D-1 category. So for D equals to 2, it's just a fusion.
Oh, right.
category.
It's D plus 1 minus 2. Thank you.
Yes.
And then BS sim is that fusion category viewed as a right module over itself? If you call it Dirichlet?
Yeah, it's actually a module over itself. Yeah, I think so. If you want to characterize in terms of, yeah, probably. I'm not sure, but it doesn't directly relate to the physics picture. So we can probably. No, so I have not described to you what symmetry TFT is, first of all. I've just said that there is this TQFT on and which admits a topological boundary, whose topological operators are the symmetry S. Right?
But there are many such, and which are the ones for general fusion category S, higher fusion category? Which is the one that you would refer to as Dirichlet boundary condition?
So you're saying given the symmetry TFT, there may be multiple boundary condition with the same, yeah. So you just pick one of them. All it does is just changes the physical boundary. So this is not unique. The symmetry boundary is not unique, as you rightly point out.
But there should be one that is referred to as Dirichlet.
No, you just pick one of them and that will be your Dirichlet, right? It's just choosing what you choose to call the symmetry S.
Thank you.
Yeah. So in S3, it actually happens. I will discuss the case of rep S3. Yeah, in that case, there are two boundaries which give you S3 and two boundaries which give you rep S3 symmetry. Yeah, and the physics is indeed quite different for the two S3s. Okay, so sorry. So let me quickly finish the general idea and then I can fill in the details after the break. So the general idea is as follows. So we said dynamics lives on the right-hand side. So let's consider some operators. So all the non-topological operators are localized there. Now suppose that, yeah. So we're considering some operator. This could be of any dimension. Suppose its lift is just like this. Then all the symmetry which acts completely on the left boundary is totally decoupled from it. So it doesn't act on it, which means that this operator, if its lift is like this, it must carry the trivial charge. So how can we obtain non-trivial charges? We need to somehow have a construction of this operator which talks to the left boundary. So the interval compactification has to involve something like this. So this operator needs to be living at the boundary of a bulk one higher dimensional operator. And then this bulk higher dimensional operator goes to the boundary and does something over there. Then it can talk to the topological operators living there. So from this picture, you can see now all the action of S on this operator is encoded on how this bulk operator ends on the boundary, on the symmetry boundary, which is a totally TQFT property. So all the information I need is what is the bulk operator to completely determine it. Then determining it might be, the whole action might be complicated, but I can at least label the charge by topological operators. So the statement that we obtain is the generalized charges are the same as topological operators. So generalized charges of S are the same as topological operators of the symmetry TFT Z of S. And then when you apply this to invertible cases, it's easy to see that you obtain higher representations again, you recover them, and you can generalize it, as I will do it after the break. Yeah.
I was saying that you'd presumably be only interested in the subset of the topological operators of Z of S that can actually end on B on the other boundary, right?
Yeah,
Because if it's only living in the bulk, but it doesn't go to the left boundary, then it's presumably again trivial.
yeah. So I suppress some details here. So when it comes over here, it might become an operator living on this boundary. Some topological operator might be attached to it. So then it goes into twisted sector of the symmetry. So here also it needs to be attached to a topological operator. So here I assumed I looked at untwisted operators, then they must be of this form. Yeah. So,
This is a kind of non-result. No, it's the fact that the two algebra representations are like simple objects in the intersection. No?
yeah, that's a known mathematical statement. Here we asked a physics question, and now we want to relate it to all these mathematical results.
Generalized charges is just another name for the two algebra, or is something?
Yeah, it turns out to be another name for tube algebra, but you need to like give some physics argument. So here you can set up the problem. If you just set up the problem on the left-hand side, you obtain tube algebra. If you go to the sim TFT and use this, you obtain the Drinfeld center description. And then the mathematical result is encoded as this general physics statement that I made over there.
Okay.
Yeah. Sure, yeah.
Today at 2 there will be another talk on instanton operators and BCD metals. And if anyone has questions, please try to use the microphone.
All right, welcome back. So I want to, in this remaining half an hour, sketch what happens for a general non-invertible symmetry, how the generalized charges are encoded, and also to describe some physical applications of these generalized charges, like so when can they act as order parameters for gapped and gapless phases, and if they act as order parameter, how they can be used to formulate a generalized Landau-Ginzburg program, distinguish different phases which are protected by a non-invertible symmetry. So I will be quite sketchy about general details. They will apply, I mean, the concepts apply across all dimensions. Concretely, I will focus only on those two cases, rep S3 and esync, to show you that all these calculations can be carried out concretely, at least in lower dimensions. And there already we learn many interesting things. Okay. So this was the general statement that we had, that generalized charges should be topological operators of the sim TFT. So again, there are some general statements that this sim TFT can be constructed as a state sum construction based on this fusion higher category. This is very well known for fusion 1 categories. If you begin with a fusion category, you can do a Turaev-Viro state sum construction to obtain a 3-dimensional TQFT. And their analogs have been proposed by Douglas and Reuter. Beginning with fusion 2 category, you can obtain a 4-dimensional TQFT. So this is what this symmetry TFT is, and for the details get complicated, but the idea is expected to hold as you go up in dimensions. And without having to do the state sum construction, there is a mathematical technique by using which you can obtain the generalized charges, because you just care about the topological operators of the symmetry TFT and not its partition functions on arbitrary manifolds, etc. So this is also equivalent to what is known as the Drinfeld center. So generalized charges are topological operators, and they are elements of another category, higher category, which is known as Drinfeld center of this. So if you have one category, this is a braided fusion 1 category. So this is a braided fusion, say D-1 category. So it includes operators of codimension 2 and lower. And this also explains all these discussions about why I'm restricting to codimension 2, because this general structure is applicable only there. No.
Some construction in the dimension.
The topological operators of that, no. So it's known in it's known that it's the Drinfeld center as it's defined for fusion 1 categories. Yeah. The question is if it's known that the topological operators of the Turaev-Viro theory will be given by Drinfeld center. So this is in, yeah, it's known for 3-dimensional symmetry TFTs. For 4-dimensional case, I don't know. It depends on whether you have an independent definition of Drinfeld center or not. But probably you want to define it in such a way that it will turn out to be topological operator of symmetry TFT. So yeah, I don't know about the specifics. So far, it's just a terminology in high dimension. Okay. So, but now we understand fusion 1 categories case very well. So we can jump to that and see what are the generalized charges, what are the Drinfeld centers of REPS3 and desync. Okay. And then we can concretely describe the actions as well. So let me begin with REPS3 case. So here there are general results that Drinfeld center does not depend on fusion categories. It only depends up to Morita equivalence. So what that means physically is that you can gauge this symmetry and you compute the Drinfeld center there if you want. So rep S3 can be obtained by gauging S3 symmetry. So you can obtain this by gauging S3, just standard group like zero form symmetry in 2 dimensions. And then these rep S3 can be thought of as Wilson lines obtained after gauging, which are labeled by representations. And then you can compute the Drinfeld center of S3 quite easily. So there are some particular, so you obtain various lines. So let me describe what these lines are. I will label them as follows. Okay, this is plus minus. So there are 2 of them here, 1 here, 3 and 3. So omega is the third root of unity, and 2 of them here. So there are a total of 8 line operators, simple line operators in the Drinfeld center. And these are all the possible generalized charges, or the charges on which S3 and rep S3 can act. So I've described them in a frame so that S3 action is very visible. So these are operators which will be, so 1 plus is just the identity operator, not charged, trivially charged. 1, 1 minus is a charge on which the Z2 symmetry acts. So these are just the representation, the usual representations we know, 1, 1 minus, and E. Then other charges are for twisted sector operators. So when we discussed earlier, we only focused on untwisted, but we can also look at operators living at the ends of line operators generating zero form symmetries. So here inside S3, I am choosing to represent it as a Z3 cyclic permutations, 1AA squared, and then a transposition B. And then there are more elements, which are combinations of this. So B is Z2 order 2, A is order 3. So there are twisted sector operators. So if you take the line A and take an operator, if there exists an operator living at the end of it, just by acting by B, you obtain an operator also living at the end of A squared. So they form a multiplet, which is what this denotes. And furthermore, when you have such an operator, you can wrap another Z3 element consistently around it, which is the centralizer of this A. And then there can be Z3 representations that this can carry, which are these omega to the I. Similarly, if you start with B, they must form 3-dimensional multiplets, and then you can wrap B around them and get a sign representation. So in terms of S3, it's very easy to understand. In terms of rep S3, it's more complicated. So these ones are simple to understand what happens to them. So now I will describe how these same charges appear in terms of rep S3 symmetry. So just these ones just become twisted sector operators. So they are attached to 1, minus, and E lines. These are now line operators generating symmetry. And these ones are quite interesting, actually. So let me focus on the first case, which has 1. So this includes an operator which is untwisted, and it includes an operator which lives at the end of 1 minus. And then these two are permuted by the action of rep S3 with some coefficients. This all can be obtained from the Drinfeld center description, mathematical description. So there are various interesting actions here. So I'm again looking at this charge A plus A squared 1. So I have to describe the major thing comes from how E line acts, this non-invertible line acts, and the action takes the following form. So it's minus half times this operator plus omega plus half times the twisted sector operator attached to the E line. And now sometimes we would like to understand what's the linking action. So we might want to understand what is the linking action of E on this. Then you can simply use this relationship to obtain it. So you just circle both of them around. This piece gets killed because it gives you some tadpole configuration, which tells you that you're looking for morphisms from 1 minus to identity, but there aren't any. So this term gets killed. And then you get you're left with minus half E times the operator itself. And the quantum dimension of E is 2. So you just get minus 1 times the operator. And this is a well-known linking action that has, yeah. But more generally, we should think in terms of non-linking actions like this, because they contain more information about the action. And from this, you can always derive linking actions. So mathematically, these coefficients are encoded in what are known as half braidings. When you try to write down Drinfeld center of rep S3, you need to choose some objects. So the object here you will choose are what are the sectors, which are the identity and 1 minus sectors. And you will choose some half braidings, which will be these coefficients. Okay, so here I wanted to show how non-invertible symmetries can force operators to be in multiplets, in interesting 2-dimensional multiplets with interesting coefficients appearing. So in this way, you can understand other charges as well. Okay, so I don't want to get there. Let me describe interesting charges in E-Sing now. So if I choose E-Sync, recall that it has one P and S, where S is non-invertible. And there is an interesting charge in it. So there is from the Drinfeld center, you can see that there is a two-dimensional multiplet. There is only one irreducible two-dimensional multiplet, which contains an operator, untwisted operator, and an operator which is in the twisted sector for Z2. And then these are permuted by the non-invertible line. So first of all, they have different charges under Z2. So P acts non-trivially on the untwisted one, trivially on the twisted one. And then the non-invertible symmetry exchanges them. So you have configurations like this. So there is the former the non-invertible symmetry acts as sigma x Pauli operator, while the invertible one acts as a sigma z. Okay, so these are some interesting charges. So how can we use them for obtaining interesting physical applications? Yeah. So in the last 15 minutes, let me sketch that. Okay, before going there, let me provide references for this general result that generalized charges are topological operators. This appeared recently in my paper with Sakura, which is generalized charges part 2. And a related paper, again by the same group, is Thomas, Matt Ballimore, and Andre Grigoletto. So that's for these general non-invertible, how non-invertible symmetries act on operators. Okay, now I want to describe some upcoming work on physical applications of all of this. So this is where the generalized Landau-Ginzburg program enters in. So we know that if you can characterize phases according to how symmetries act on local operators in the infrared. So for example, the usual thing is that in any dimension, if you have a Z2 symmetry, you have an operator in the ultraviolet, which gets a wave. So if this gets a wave, and it is charged non-trivially under Z2, so Z2 action is -1 on this operator, then you can conclude that you will, and you know that your theory is gapped in the infrared, then you can conclude that there will be two vacua in your theory. So this becomes as an order parameter. If it's if there is no such operator, then there will be a single vacuum in the infrared. And the key point that went into it is whether there is an operator that survives in the infrared or gets a wave, non-zero wave. The operator is charged under this symmetry. So now we want to find a non-invertible generalization of this. So I want to replace this by some symmetry S. And I want to ask, can I characterize gapped and gapless phases by some charges that get some charges that get a wave or not, or more precisely, whether there are operators carrying certain charges which get a wave or not. Okay. So here there are constraints on. There are interesting constraints you can obtain. So let me study first gapped phases. So I want to first study gapped phases protected by S. or in high energy language, I'm studying TQFTs such that S is a symmetry. And I can use the general sim TFT prescription now. So such a thing will be equal to, I can resolve it into the sim TFT, the symmetry boundary condition, which was topological, and the physical boundary condition, which was in general non-topological. Since I want a topological theory on the left, I must require this to be topological as well. So this must be topological. So if I want to classify gap phases protected by S, all I need to do is classify topological boundary conditions of the symmetry TFT. So we can do that in our for example, 2 dimensions. So there it's known that such topological boundary conditions correspond to Lagrangian algebras in the Drinfeld center. And then these Lagrangian algebras are just some objects in the category. So there are some objects, some lines, line operators in the 3-dimensional bulk. And these line operators were precisely the generalized zero charges. And then what it means is that if you are in a phase which corresponds to this Lagrangian algebra, then you have in the U ultraviolet, you had some operators which were carrying the generalized charges given by Li. So this matches whatever. So why is that the case? It's because these generalized charges survive in the infrared theory, which is precisely what it means to have non-zero wave in the ultraviolet. I think I don't have a reference in the mind at the moment. I thought this is something which is well known in the community. Maybe I'm missing some subtleties. Is that what you're saying? Or no, just okay. No, I don't have a reference. So there are general things, right? So all the topological boundary conditions are related by gauging by Morita equivalences. The categories living on them are related by Morita equivalences, right? And that corresponds to, yeah. Okay, I'll get. Yeah. You mean like a sum of boundary conditions here?
Is the correspondence so okay? Okay, maybe it's a stupid question. So let me ask another question instead. So what you want to consider here is a line Li which stretches between the 2 boundaries. This is what you want to do now.
So I'm asking what are the lines Li which can end on this boundary?
But they have also to end on the other side because
they
otherwise
may or may not, because they might be twisted sector operators. So these multiplets might contain twisted sector. So this line Li might become some line or might not.
Okay.
But then you still have, you mean that this means that in the infrared you have this twisted sector and twisted sector operators.
Yes.
Yeah.
Okay.
Thank you. First, there's a reference by Xiaogang's paper, recent paper, maybe with Lakshya. And another thing, our community, we would say that all the gapped boundaries, all the gapped faces corresponding to this Lagrangian algebra, but some of them actually breaks this asymmetry, for example, spontaneously.
Yeah.
If, for example, if it's like all charges, pure charges in this Drinfeld center is condensed on the boundary, the symmetry is totally broken.
Yeah.
Yes.
Right. So there is yeah. So this phase, for example, was a spontaneously broken phase. So when this happens, the gap phase would be Z2 SSP. This is the terminology that is often used in condensed matter, and there is similar. You can generalize this terminology to non-invertible cases. Yeah.
So once the SSB has happened, you'd get like a multi-fusion category on the right boundary, right?
No,
Because you don't have a unique vacuum anymore.
No, it's you get topology, you get multifusionness on this side because you have multiple local operators stretching from lines. So there is a line which can end here and here. It gives you an extra local operator, topological local
I
operator.
see. So there's a line that stretches between them now.
Yeah.
Okay.
Yeah, which
So
is
in
the corresponding to the charge. Okay,
Thank you.
so
That's helpful.
so I will now rush a little bit because I only have like some more minutes more than 5. Okay, so let me describe how it works out for rep S3 and eSync concretely. Okay, before going there are already some criteria because I mentioned gapless phases. There are already some criteria. So some of these lines cannot appear in any Lagrangian algebra. So what that means, if you have some operators carrying those generalized charges and they get a web, then the theory in the infrared cannot be gapped. So that's a criteria for obtaining gapless phases. And this will appear in our in a work soon. So they can be thought of as order parameters which are enforcing gaplessness.
Practice, you look at the guys who have speed of 1 above.
Yeah, in the group like case, that's the criterion. Yeah. Okay. Okay, so now let me focus on gapped phases. So these kind of gapless things one can classify. Now let me focus on classification of gapped phases. So again, let me start with rep S3 on this side. So there are 4 boundary conditions given by 4 Lagrangian algebras. I can quickly write them down. So they in the previous notation, they are something like this. And there are 2 more. So maybe 2 and 2 and yeah. Okay, so there are 4 such Lagrangian algebras, which tells you what are the generalized charges which are acting as order parameters. These are the generalized charges. You know how their action should be, and all you want to do is represent all these actions on a gapped phase, right? And then, or you can use the symmetry TFT to obtain some understanding of them. And then you find 4 phases protected by rep S3, for example. You can give them interesting names. So they correspond to the 4 phases, which can be thought of as, they're not in one-to-one correspondence. There's some correspondence here, but we can characterize them as follows. So if one of them, rep S3 completely breaks, and in one of them, Z2 inside the rep S3, Z2 subsymmetry is spontaneously broken. In another one, rep S3 mod Z2, so just the non-invertible piece is in some sense broken. And the other one is trivial phase, where everything is preserved. And then you can count the number of vacua for them depending on how many lines are ending on both boundaries. So there are 3 and 3 for these, there are 2 and 1. So there are 2 phases which have 3 vacua, and they're actually different in the infrared. So if you look at the TQFT in the infrared, this one is pretty standard. It has all the 3 vacua on an equal footing. In this one, there are 2 vacua. So let me label vacuas like this, which are on which Z2 is spontaneously broken, and on one of them Z2 is preserved. So from the point of view of the subsymmetry, it looks like a spontaneously broken and preserved phase, and there is a non-trivial relative Euler term between them. So there is an interesting structure in the infrared, which is encoded in the quantum dimensions of the interfaces that go between these vacua. Okay, so no, these are not in correspondence. Yeah. Yeah, E-line maps between them, and that can be seen as an action of E line on generalized charges. And now similarly for E-sing, maybe E-sing is the more interesting. So for E-sing, one can figure out the same thing. So it turns out that there is only one gapped boundary. So for E-sing, there is only one gapped boundary of the sim TFT. So whatever symmetry boundary you put here, your physical must be the same as symmetry as well. So there is only one gapped phase. You can count how many vacua it has. It has 3 vacua again. And now again, from the point of view of the Z2 subsymmetry, it looks like a Z2 broken and a Z2 preserved phase. There is again a non-trivial Euler relative Euler term distinguishing the two things. But here the Euler term is different from that case. So there it's 2 and here it's square root 2, which captures the quantum dimension of the non-invertible element. So they are different in the infrared as symmetry protected phases. And then, yeah, the non-invertible symmetry exchanges them. So you can give some physical understanding for that. This non-invertible symmetry is a Kramers-Vanier duality. It exchanges low and high temperature in the E-sing model. So it should precisely interchange spontaneously broken and preserved phases of the spin flip symmetry. And so now if you require this to be a symmetry, you must have both of those phases simultaneously. So these are some of the results, concrete results. And in this case, the Lagrangian algebra looks something like this. There is a 1 minus representation, and there is this non-trivial exchange representation that I described earlier, which contained an operator and a P operator, which are exchanged by S. Okay, so I think I'm running out of time, right? Yeah. Okay. So since I have a few more minutes, I can describe generalizations to higher dimension. So in higher dimensions, you can follow the same logic, but the story becomes quite complicated. So let's say we are in the space-time dimension 3. And even if you focus on Z2 zero form symmetry, so you say S was just Z2, you want to now take the symmetry TFT, which is a Diagraph-Witten theory in 4 dimensions based on the Z2 group. So this is Diagraph-Witten based on Z2. You want to classify it's also known as the 3 plus 1 dimensional toric code. And now you want to classify its boundary condition, topological boundary conditions, but there are infinite number of simple ones. Which again has to do with the fact that there are many fusion 1 categories, infinite number of them. Okay, so you can try to classify based on some rank. So you can first of all do a classification. The classification becomes something like this. So you pick some modular tensor category. We're classifying gap phases. So that's your underlying 3D QFT, and you want to represent Z2 on it. And using this, one can start classifying various different kinds of toric codes, Z2 protected toric codes, for example. One can generalize this whole story to one form symmetry or representation symmetries. But the main problem we are dealing with is pick a 3D QFT. There are infinite number of them, and then you want to see for each of them how many protected versions of it are there under that symmetry. Yeah. Okay. So let me first conclude, then I can take questions. Yeah. So let me conclude now. So non-invertible symmetries have been explored a lot recently, especially in the last 2 years, in the context of higher dimensional non-topological theories and topological operators inside them. One of the most important questions is to use these symmetries to obtain physical applications. And if you think about it, all these physical questions, if you want to analyze them systematically, you need to understand how these symmetries act on your theory, or how do they act on the observables of the theory. One particular class of observables are operators of various dimensions. So one wants to understand that first of all. And as I proposed in the talk today, these operators form generalized charges, which can be divided into Q charges based on the dimensionality of the operators. And one can characterize them as Q plus one-dimensional topological operators of a TQFT, which depends only on the symmetry, which is known as the symmetry TFT. And from this, just using TQFT knowledge, you can obtain the full understanding of these generalized charges. Then one of the physical applications you can look at is how is infrared phases, whether they be gapped or gapless. Then depending on whether these generalized charges may then condense or not, they may get a wave or not. And depending on that, you will get gapless or gapped phases. And you can distinguish different gap phases depending on which generalized charges are there in the infrared. So this leads to a generalized Landau-Ginzburg program for non-invertible symmetries. And thank you very much for your attention.
Yes, sorry, I had a question. I agree that for D equal to 3 or greater, any topological quantum field theory has an infinite number of simple boundary conditions because you can stack TFTs on the boundary. But I think you can always take equivalence classes up to stacking, and you will get a finite number of simple boundary conditions if you take these equivalent classes. Am I right?
Yeah, but I think there is still an infinity, another one, which has to do with the fact that they can also interacting boundaries as well, because you can choose any underlying 3D TQFT. So you first pick some topological order, and then you ask, can I symmetry protect this topological order, and how? And then it will and for each topological order, you obtain some finite number of cases in which is symmetry protected versions. So like for toric code, you obtain at least 6 of them, different versions of toric code protected by Z2 symmetry. Yeah.
But do you mean on the boundary or on the bulk? You choose a topological order?
Yeah, I mean like this is after compactification.
After compactification.
Yeah, there's still this choice of underlying 3D TQFT, which is an infinite number of them.
Which are decoupled from the rest?
No, this is the gapped phase in the infrared. So I'm just directly dealing the problem without using SymTFT. If you just directly look at the problem, it's you first of all have to pick a gapped phase without a symmetry. Then you need to tell me how symmetry acts on it. So just gapped phases without symmetry, they're an infinite number.
Okay, but could I think this like additional topological order is living on the physical boundary?
Yeah, it's in some sense, but it will extend into the bulk as well.
Okay.
Yeah. Okay. Yes.
I also wanted to ask about this. So you said there's an infinite number of equivalence classes of simple objects somewhere. Which is the somewhere?
The fusion 1 category. So three vector spaces.
I don't understand.
So if you look at simple objects of three vector spaces, there are infinite number of them. They correspond to fusion 1 categories up to Morita equivalence, I think.
So you consider modular fusion categories as objects in a 3 category, and they're simple there?
Yeah, so here, if you want to be precise, I shouldn't have said modular. I should have said Drinfeld centers of fusion 1 categories. So it's just to connect more to physics audience, I said modular. Because I want to work with TQFTs, which are in the bosonic world are completely defined in 3 dimensions, and they don't need a 4-dimensional extension. But in general, for modular categories, you need this. You have a 4-dimensional invertible theory that comes attached to them.
So you say you have a nice braided 1 category, for example, the Drinfeld center of something?
Yeah, this should be replaced by Drinfeld center of a fusion 1 category.
And this is a non-topological 3D theory?
No, topological.
It's topological.
Yeah, because we want to classify gapped phases protected by symmetry. So we pick some TQFT, 3D TQFT, and we want then to implement symmetry on it.
And all of them are boundary conditions for Z2 Dijkgraaf-Witten theory in 4 dimensions?
Yeah.
I see. Thanks. Also, I wanted to ask, what is the Euler term for you?
Right. So in 2 dimensions, there is you can have partition functions. So there is an invertible 2D TQFT whose partition functions are of the form this. And if lambda is in R plus, is unitary as well. But usually you don't account for them when you consider phases because you can tune lambda to 0. So it's not in the deformation class, it's just the same as trivial. But if you have symmetry, then you might not be able to tune this. So there is some square root 2 lambda parameter that is left over, and you cannot tune it to 0. Yeah.
Thanks.
Yeah. Sure, it is coming to you.
So I thought that on the TQFTs, no, the symmetry action corresponds in 2D. Let's do 2D. Okay, corresponds to having a NIM representation for the fusion algebra. So integer valued representation because you act on the vacua, no? And is it obvious that every representation of these higher charges or this tube algebra descends to some NIM representation? Because it might be that you have this representation, like you can have a one-dimensional higher charge, but you don't have one-dimensional NIM. So I would say there is no TQFT with one vacuum then.
So it's possible for, yes, so for example, in the Ising case, there is no TQFT with single vacuum.
But there is no NIM representation for Ising.
Okay.
There is only, this one is the smallest one you can build.
Yeah. So NIM representation is you want to just forget about the categorical structure and just remember the fusion ring.
Yes.
And you want to implement that. So certainly, but we want a categorical representation, right? So certainly every categorical representation will give a NIM representation, but it may not be true vice versa. And so for example, you can just take vec Z2, just Z2 symmetry. No, not Z2, Z2 times Z2, let's say. So now there is only one NIM, there is no NIM representation for the SPT phase, 2D SPT phase, because that's a categorical representation. Right, so there is no one-to-one correspondence. So there's rather a map from phases to NIM representations. And this map is neither injective nor surjective.
I thought when you have a phase, when you have a gapped phase, you have a NIM representation, which is the action, but okay, it's not.
Yeah, and it's neither injective nor surjective. I don't know about surjective, by the way. Yeah, so okay.
Okay.
Thank you.